Hello everyone, welcome to Coders Camp. We are at the 20th day of May LeetCode challenge, and the problem today given is binary tree level order traversal. So the input given here is a root of a binary tree, and we have to return the level order traversal of this binary tree. So here is our given binary tree. Level order traversal is nothing but traversing the binary tree level by level. So first, starting from the root node, at this level 0, it has only one node. So the result is going to have the lists of lists, and each list in the result is going to have the nodes at each level. So for level 0, at result list, the node is going to be 3. And moving on to level 1, there are two nodes at level 1 and they are 9 and 20. So again, we're going to add one more list with 9 and 20 as the value. Finally, moving on to our level 2, and the values present in this level is going to be 15 and 17, and that is going to be added to our result. And finally, we are going to return this list of lists as our output. So this is a very basic traversal technique of a binary tree where we have used breadth first search to solve this problem. So if you are following LeetCode problems for a few months now, you must be familiar with what is a breadth first search, and you must have used this technique to solve many number of problems. If you are not familiar with what is breadth first search, this is a nice time to learn what is the traversal technique to traverse a binary tree, and by using these technique and these code you can solve many problems related to a binary tree. So let's dive in to understand how breadth first search works. So we have two different traversal techniques for a binary tree. One is depth first search, and the other one, which we are going to cover in this video, breadth first search. So DFS always need a stack to work iteratively. Same way our BFS need a queue to work iteratively. So here we are going to cover the iterative approach where our queue comes to help. So here we are going to perform level order traversal, and as per the problem statement we have to return a result in the format of list of lists. So in that case we are going to maintain a list for each level. So once we covered the nodes at that level, we are going to add that list to our result list, which is actually a list of lists. So starting from a root node, we are going to traverse a root node. So we are going to push that node to our queue. So once we put that to our queue, we know that element is going to be at that particular level. So we are going to get the size of queue, and you will understand why we are going to get the size once we go half of the algorithm. So now the size of the queue is going to be 1, and we are going to add that node to our list. So let's add 3 to our list, and our list should have integer value. So here instead of nodes, we are going to add nodes value. So once added, we are going to explore its children. As per binary tree will have two children's max. One is left and other is right. So here in this tree we have two children, which is 9 and 20. So we are going to add them to our queue. We add 9 and 20. So now we have added its children to queue and added its value to the list. So we are done with the job of 3. So it's time to pop 3 out and move the nodes to the front. We have now 9 and 20 in our list. Now again it's time to take the size of the queue. So here the size of the queue is 2, which actually means there are 2 elements at that particular level. So you don't have to really move ahead and check the other elements because this level ends with 2 elements. So before moving to the next level, we have to add the list to our result list, as this is one level of values. So now in next level we have two nodes 9 and 20. So it's time to explore first node in the queue. So we are going to add 9's value to our list. So if you check in our tree, we don't have any children left for 9. So in that case, we have added the values, explored its children. So job of 9 is also done. So pull the value from our queue. And now our 20 comes into place. So now we are exploring or traversing the node 20. So add the value of 20 to the same list. So once added, we have to explore its children. So in this tree, we have two children, 15 and 7. So it's time to add 15 and 7 to our queue. So the job of 20 is also done. We have added the value and we have explored its children as well. So it's time to remove 20 from our queue. So once 20 is removed, we still have two more nodes left. So before exploring those two nodes, it's time to add that particular list to our result as that level is done. So now we have added that to our result. Finally, we have two more nodes in our queue, which is also of size 2. So this is nothing but we have only two nodes in that particular level. If suppose we had children for 9, say 2 and 3, that would be added in front of our queue, then our size would be of 4. So in that case, we will be exploring 4 nodes and add its value to the list as 4 nodes. But here we have only 2 nodes left. So now first explore the top element in our queue, which is 15. So time to add 15 to our list. So once that is added, we are going to explore its children. 15 doesn't have any children, so we don't have anything left to add to our queue. So 15's job is done. So time to remove 15, and we have only 7 left in our queue. So it's time to explore or traverse 7. So let's add 7 to the same list of that level. So once 7 is added, we are going to explore its children. 7 doesn't have any children, so we don't have anything left in our queue to be added. So we are done with 7 as well. So let's remove 7 from our queue. So we are done with that particular level. So attach that list to our result list. So once that is attached, our queue is now empty. We don't have any other nodes to traverse. So yes, we have traversed our complete binary tree, and this is going to be our output, which is nothing but the list of lists of node at each level. So this is a basic BFS technique. This is how a breadth first search works. We can solve a lot of problems by using the same technique and also using the same code pattern. So before getting into the code pattern or the code for this particular algorithm, let's understand the time complexity. So we are going to traverse each node only once, add them to the queue, and we are simply adding them to the list. So once we are traversing all the nodes, so it is actually going to work in linear time, which is nothing but big O of 1. And also we are going to have a space of big O of n, which is nothing but a queue. So it is going to work in a linear time and space complexity. So let's go to the code now. So yes, in our code, I have declared my queue already, which is going to hold the tree nodes, and my result list of lists, which is what we are going to return finally. So here first in my queue, I'm going to add my root node. Before that, I'm checking whether my queue is not empty. So if it is empty, so simply return our result. If not, we are going to add a root node to our queue and iterate till our queue becomes empty. Inside, I'm going to declare a list which refreshes every time we explore a new node or move to a new level, which is going to hold the integer values, as we have to return only the values, not the tree nodes. So let's take the size of the queue for that particular level. So we are going to iterate a for loop for that particular size, because we need to explore only that many nodes for that level. So you can ask me a question, why do we need to declare a variable and then assign the value? Instead, we can directly put q.size here. So, and this variable is unwanted. If you think that way, once we explore the node and add its children, the for loop is not going to stop, because once the children are added, q.size is going to increase. So before increasing or before adding the children, we need to have a variable which stores the current length of the queue. So once that is added, we are going to take the current node in the top of the queue. So as I said, first we are going to add its value to our list. Once that is done, we are going to explore its children. So yes, once the iteration is completed, we have to add that list for that level to our result list. So once that list is added, every time a new level is explored, our list is going to initialize fresh and add nodes for that particular level. And finally, our result list is going to have the list of lists. So let's run and try. So yes, let's submit. Yes, the solution is accepted and runs in 1 millisecond. So thanks for watching the video. Hope you liked my explanation. If you like the video, hit like, subscribe, and let me know in comments. Thank you.